the voltage equation and the current equations on the high frequency transmission line. To understand this, maybe this is only the result using Z as the component. But if you want to know about the total voltage and the current with the component of Z and the T, you need to time this one to multiply these two equations to exponential by J omega T times exponential J omega T to these two components. Then you will obtain these two equations with respect to, they will have the variable of Z and T, okay? Just multiply this term to this one, and then you will have the voltage is the component of Z and I. Okay, they are the structures of the voltage and the current on all the high frequency transmission lines. Okay. Do you need a time to write down? Actually, I have PowerPoint. You can review all I just said. You have telegrapher equations. You take, see, I just point out everything you already learned. Okay, so you change this one to only the component of Z. Change one to the function V of Z and I of Z. And also you transfer the partial differential to T to J omega. Then you will have this equation become this equation, similar to they wrote down on the whiteboard. And the second equation will become this new equation. Then you take another differential to both parts and change this term to very similar thing. What we need to do is we redefine this part to gamma square. Then you can obtain your new equations for V and I. Then you can obtain your structure of voltage and current. Okay, can you follow? Okay, I think if you pay attention on the chapter 1, this part will be easy, right? Much easier because there's no vectors, just only the scalar functions. And just this is to remind you, this is the formation for the E field, right? And we will have a formation of the voltage and current. Okay, so what is gamma? We define gamma, the propagation constant, equals to the square root of these two parts, right? And you remember what is R, what is omega, what is L, and what is G, what is omega, what is C. Okay. For the same uniform transmission line, they have the same R, L, and the G and the C. If you have different frequency, because omega equals to 2 pi times frequency, so if you change the frequency, the gamma is changed. Furthermore, as I said, because gamma equals to alpha plus j beta, if R and G equals to 0, if you don't have R and G, you don't have alpha, gamma will equal j beta only. And this is lossless transmission line. If you have a question, the question write down, it is a lossless transmission line. It means gamma equals to j beta only, and it means R and G is that both of them are 0. Okay, if you see on your question, this is a lossless transmission line, 0 and 0. Okay, this will be the easiest case. Okay, are we okay? So gamma equals to j beta, and this gamma equals to j beta. Then our equation becomes easier. J beta. Okay? If this is a lossless transmission line. Okay, so next part, we try to define the ratio between these terms. Because the total voltage equals to the forward voltage plus the reverse voltage. This is a different direction. This is the voltage going to positive Z direction. This is the voltage is moving to negative Z direction. Okay, the voltage, and the same. This is the current moving to the positive Z direction. Current move to the negative Z direction. We want to define something. It is the ratio between these two terms. The ratio between one direction, the positive direction of voltage, to the direction, the positive direction of the current, because these two terms are the same, right? We defined this to the Z. 0 and O are different. You need to very carefully to put this is 0, this is O. Okay? Sometimes it's other mode. O means characteristic impedance. Okay? This is a definition. Just only one direction of voltage to the ratio of voltage to current. Okay? Because for a transmission line, voltage here and the voltage here, okay, looks the same. the forward voltage and the reverse voltage looks the same. So you don't see the negative side. But for the current, it's different. If the current here is going to this direction, the current, if that the reverse current is going to, should be forward, reverse. This one is going to this direction. Okay, so your characteristic impedance is also the ratio of you need to put a minus sign here. This is very important. For the positive, it's okay because the voltage is the same. But for the current, the forward and the reverse current, they are different. Can you understand? The voltage is the same everywhere. Okay, but current is different. So for this part, you must put a negative sign. Okay? Very good. So this is the definition of the characteristic impedance. You can directly put this equation here because you already know voltage, right? When you take the different partial respect to z, you put your result, your voltage here, this part can become this one. Okay? Look at the V. For this equation, after all, you got this result, right? You already know this one. Then you take this result back to your first equations. You take the partial term respect to z to your result equation, okay? And you keep this the same. You don't change anything for this part, but you change this part because you already know what is V, okay? Then you can obtain this part. Okay? Then you separate this equation with the first part with exponential to the power minus gamma z. So you will know this term equals to this term. Then you obtain your z0 equals to this one. Okay, let's do that together. This is, I think, okay. Can anyone want to do this? Wanna try? No. I will give you advice. You just follow my direction. Okay? You can follow my guidance. First, you change this equation. Yeah. Change the first equation to use the voltage there. Yes. Okay. Don't need. Yes. Okay. Then do the first part. Yeah. I give you 5 points. You just derive all that. Yes. Yes. So just write down, do the first partial equation. Okay, just that's it. Okay, then write down what is I. Yes, just copy this one, but change Y. Change your current to the result. Okay, then you separate this term. You have an exponential to the minus gamma z equals to this term times this part. You separate this part, and this term equals to also this term times to this part. Okay? Then, because we define this term equals to z0 equals to minus you use these equations, then you can obtain so this one, according to this equation, equals here, and the gamma equals to the square root of this term. This is gamma, right? So finally, we obtain. This is the result we want to obtain here. This is a characteristic impedance And this is the 15 ohm we always use. It is very common. You say, oh, 15 ohm, right? So sometimes we use this one very often. So this is the definition of the characteristic impedance, and what is the characteristic impedance of a transmission line. You will use this one. But the question is, what are R, G, L, C? What are they? This is the question, right? You don't know. You don't know. So actually, there are equations. This is a coaxial cable. Coaxial cable. If your inner radius is A and outer radius is B, you can obtain your inductance per unit length and the capacitance per unit length as these two equations. If this is a lossless transmission line, then you can put R and G equals to 0, and then you use this one. So, what is the characteristic impedance for coaxial cable? Can anyone give me an answer? 5 points. For coaxial cable, for lossless coaxial cable, Z0 equals to what is coaxial, lossless coaxial cable? What is that? 5 points. Everyone? Anyone? Just raise your hand. This is 0. This is just mu, and this is epsilon. I think the same as what we say in chapter 1. Points. Come, just write it down. 10 points. Z0 equals to 10 points, because this is important and a little bit difficult. Write down. Why? No, you need to derive it carefully. Yes. Are you sure? For a lossless transmission line, Z characteristic impedance equals to, can you do that? Step by step, don't be hurried. The first step, what is okay, go back to the here. See? Use this equation. Okay. Okay. If this is a lossless transmission line, that's it. Equals to okay. Then wait. For a coaxial cable, L equals to yeah, 10 points. Well, that's an easy point. Okay, and this one equals to yeah, very good. 10 points. Okay, excellent. Okay, if you have a coaxial cable, the cable has some material between two conductors. There's an inner line and the outer shell. Okay, there are something between that. If that is air, mu equals to mu 0, epsilon equals to epsilon 0 if this is air. But if that is Teflon, it is 2 point something for the epsilon r. Epsilon become 2 point something times epsilon 0. Okay? And the mu, we usually use mu equals to mu 0. So, for this part, and this part means your structural dimension for your A and B, the radius, the inner radius and the outer radius. Okay? 2 pi is a constant, mu and epsilon according to material. So after you know the geometry, you know the characteristic impedance for cable. This is how we calculate. We can ask Zhixin, right? Do you remember you don't know the equations when you do the 顺态产学? We use this equation a lot. We try to calculate the characteristic impedance. You don't know? Okay. This is the equation we usually use for the coaxial cable. Okay. If you have a textbook today, you can check chapter 3. Chapter 3. For the part of coaxial cable, you will see this equation for Z0. This is chapter 3. Anyone see that? Check the coaxial cable. Actually, we are learning chapter 2 and 3 together. Which page do you have the? Show me the. Can anyone have a? You don't have textbook? No. Chapter 3. Do you have yeah, okay. 3.5. Yeah. Now, just take a break and I will check. Okay.